Grazie.
I understand that part.
So pleased for the invitation. I'm glad to be here, see such a great crowd. There are several ex-postdocs and students in the audience, Mead and Faye, and I think Shirama is back there. And I also, whenever I come down to UCLA, I'm glad when Yuta Pearl shows up at one of my talks, and a real inspiration of my career, and I see Yuta back there. So just to acknowledge all of you. So let me jump in and start talking about these issues. So data science is a word you'll see in the newspaper. Even more, I think, than machine learning and big data, I think this word is taking over. And I want to kind of try to give some intellectual substance to it. I think it's real. I think it's a real phenomenon. I think it's just getting started. So for the young people in the audience, I think this is a fantastic time to try to think whether this career would work for you and see what the problems are that you might want to work on. So I'm going to jump in with the first page being a little bit of kind of history, if you will, from my personal perspective of where this word has come from and why it has intellectual substance to it. So I think maybe 15 to 20 years ago, I started to hear about vast amounts of data being collected. And for me, the interest wasn't just the size of the data and how fast it was coming and these kind of things that you will read about all the time these days. That's the big data phenomenon, is the wave of data and the size and the scale and all that. It was why did you collect the big data and what was the inferential problem you're trying to solve. So this talk is all going to be about the inferential side of big data. And so the statistics meets computer science. In the kind of first wave of this, it was especially the particle physicists were noticeable in collecting big amounts of data. So for example, is there a Higgs boson or is there not? Okay, so they collected huge amounts of data to test that hypothesis. The inferential problem is a classical hypothesis test, 1 or 0. So why do they have to collect so much data just to say 1 or 0? Well, because they were out in energy regimes that were never been explored before, and the null hypothesis was a particular density curve of a particular shape under the standard model, and the alternative, that's a Higgs boson, was the same exact density curve with a tiny little extra blip that was expected. Right? Now there's all these nuisance variables. When you blow up the energy to be so much, all kinds of other variables will be fluctuating around. And to see that little blip reliably and make a correct decision required huge amounts of data to get the error rates to be small. Okay? Next stage of the rollout, I think, was some of the other areas in science, astronomy and genomics. Let's collect huge amounts of data so we can find brand new phenomena the next generation of scientists can study. So this wasn't where the particle physicists were, but this is where the genomicists were and the astronomers. Okay, so now they also were collecting huge amounts of data. So from some point of view, it looks just the same. It's huge amounts of data, and every day more and more. But inferentially, it was completely different. So these people were trying to find new hypotheses. So there's maybe 3 billion hypotheses that are worth considering, and of those, find a few thousand maybe that seem plausibly worth pursuing. So this isn't just a test of a hypothesis. This is more like a discovery process and trying to guarantee that the number of false discoveries you make is small. So inferentially, completely differently. All right, so that's kind of maybe 10, 15 years ago. Then all the internet activity sort of became prominent to many of us. Google and Facebook and Amazon and so on, collecting massive amounts of data. And now, again, it was massive amounts of data, but inferentially it was really very, very different. So the word personalization is important here. So every service in Silicon Valley that was offered, search, commerce, et cetera, now became personalized because they had enough data to offer a different service to every individual, roughly speaking. Now, there's going to be huge amounts of data about some people and very little data about large numbers of other people. There's going to be these long tail phenomena. So inferentially, the problem is to do good service to everybody, even though you have very different amounts of data for each individual. Okay, so now you have to think about not just a bunch of separate hypotheses and a bag of hypotheses. You have to think about interrelated hypotheses among huge collections of people and very heterogeneous data. All right, so that now the inferential problems become really, really interesting. Heterogeneity, sampling frames. You don't know how many people of each kind of subpopulations you've got in the original data. That you have to take that into account, and so on and so forth. Okay, so I could go on and on. This became more and more interesting over time, but I just want to emphasize the data came from someplace to solve a particular class of problems. And that's what I'm going to partly mean by inferential. What are you trying to get at when with that data? All right, of course, then there are all the computational issues of how do we build a system that will scale to do the kind of things that we hope that we can assert are doing solving inferential problems. All right, so let me bring this home in a maybe more pungent way by imagining a conversation I'm having with a student who's leaving Berkeley, an undergraduate student who's starting a job in Silicon Valley. On the first day, the boss says to them, I want you to build a big data system, whatever that might mean, that will replace our classical service with a personalized service. Okay, so this kind of is a statistical problem. The classical service is probably like Google search or something. It's based on data analysis. They have a bunch of parameters that they adjusted based on data to make the search better and better over time. So that's statistics. All right, personalization just means I'm not going to have one big model for everybody. I'm going to have maybe hundreds of thousands of models for different types of people or for each individual. Okay, so I could probably do that, especially if you give me enough computers. I just do that same model, I copy it over and again, and I take each of the data, and I personalize, and so on. So, it feels hard and challenging, it'll take a couple of years, whatever, but not impossible. But the problem gets worse, which is that I need this model to work well for everybody. I can't tolerate, say, 5% error rate, like the classical statistician error rate. All right, so I need it to work well for everybody, because if 5% of the people are getting bad service, they're the ones who are going to write to the newspapers, and your business is going to look really, really bad. It's just not going to work. So this is pretty different from a classical statistical setup where we talk about L2 norms and L1 norms. It's like L infinity norm. This is like everybody has got to be served well, up to a few. Okay, so that starts to get hard. Now it gets only worse, because that's kind of just the statistical side. Now we got to bring in the computer science side, which is that the classical service ran in some amount of time. There was a temporal budget. Maybe it was Google search. It was sort of tens of milliseconds. You hit a button, and in tens of milliseconds, you got an answer. Right now, suddenly you're rolling out this new, better service that's personalized, but it can't get worse on some dimension. It can't be slower. All right? Because if it's slower, people are going to say, well, something got worse. I'm not happy. All right? So it can be slower. Now think about what you're having to do. You're trying to serve hundreds of thousands of models, all of which have a certain statistical accuracy in the L infinity norm. All right? And the algorithms have to run to achieve all those things. All right? And there's huge amounts of data. How possibly you could build a system that makes the runtime the same? Because in fact, all the kind of statistics and including the machine learning side of the field don't talk about runtime in any kind of systematic engineering kind of way. They just build a system and hope it runs at a certain speed. If it doesn't, they try to make the system better. There's no design principles. All right, now it only gets worse. And now I think it starts to get now clear that this is an intellectual problem and not just a kind of let's hope and try out and we really could do it, but it just requires effort. Okay, today we have maybe petabytes of data, and we could build models of a certain level of accuracy and so on. But in 10 years, we're only going to have way more. We're going to have 10 times, 100 times more data. Surely that can only be better, because data is what we're building this whole business on. It's our resource. So you bring in more of my resource, my performance should only get better. All right, but algorithms run slower if you give me more data. And I was going to put a guarantee on the runtime. So suddenly I can't do that anymore. So I have to maybe throw away the data at some rate or simplify in some other way. And now it becomes completely ad hoc. Now we really don't have design principles. How could you throw away data and still achieve the same runtime while your accuracy continues to get better and better as you get more and more data over time? All right, so now, as academics, we should perk up and pay attention, because we have no engineering field that can deliver these kind of things. We have statistics, we have computer science, and so on. We have principles, but none of them talk about the concepts you need to build an engineering discipline. So I like to think about kind of building buildings and building bridges. Human beings have done that for thousands of years, and they worked, people got across the bridges, and they lived in the buildings. But occasionally they fell down, and people died. And eventually a field developed called civil engineering that developed actual principles for doing those things under certain guarantees with the wind, certain levels, and so on and so forth. We don't have nothing like a civil engineering of big data. Okay? We have nothing like that. We're back in like 3,000 years ago where people would build stuff and hope it worked. And it only gets worse, because the boss says, well, also, by the way, there's privacy concerns. I'm Uber or whatever. People worry about if I use my data that they'll learn things about me. So do the data analysis, but also give some guarantees of privacy. Right? And there are many other kind of externalities like this you could list. So now the problem becomes really, really interesting and challenging. And people are trying to do this in industry, but they're doing it in an extremely ad hoc way. So that's where we are as a society. And for things like getting people around in cars, it's maybe not life or death, but think about personalized medicine and think about all kinds of other infrastructure issues. Building systems and hoping they're going to work is just not where our society should be. A lot of people are going to die. And a lot of bad personalized medicine decisions are going to be made where you tell people to do something which leads to human trauma. So we need to build something better. All right, let me say this in yet another way, sounding a little more academic, which I believe this really requires this several hundred-year traditions to come together. So computational thinking, let's say it started with Turing, but we could easily go back 100 years before that. Abstractions, modularity, logical thinking, and so on. That's a style of thinking that leads you to be able to build certain kind of artifacts. I view it as different from inferential thinking, which is another tradition that goes back hundreds of years, that has often to do with not just process the data, but think about what came before the data, what led to the data, right? And putting those two together, I think, is actually what is missing and what's needed. So what do we mean by computational thinking? I think, in a building like this, you all know what we mean. It's what's taught in a good computer science class. Inferential thinking may be less familiar in this audience, but it's always about going behind the data. What led to what was the real world phenomena behind the data? What was the sampling pattern that gave rise to data? The mathematics is often that of inverse problems. Okay, so a lot of people claim to kind of put these things together because they run machine learning algorithms on big data. Isn't that inferential computational thinking? And I'm going to argue that it's not. Very few machine learning people worry about actual confidence intervals because most of them don't worry about life and death decisions. Right? Whenever you go into a doctor's office, and you will in the future, and they'll say, well, I looked at your genome and I did this test here, and the results came out to be 7.02, and if the number's over 7, we have to do a heart operation tomorrow. Okay? That's exactly what a lot of people will be told. You say, well, what's the error bar on that? Right? Shouldn't I get some more data or second opinion? And they say, well, we don't know about error bars. We just have a black box neural net. We put in something and out came 7.02. All right? So you are going to want to know about confidence intervals to make real life decisions that actually matter, life-death decisions, not just Google search. All right, yet one more slide on kind of the philosophical underpinnings of my talk. So if you look at computer science statistical theory, there are beautiful theories, 100-year-old theories that have been developed. In statistical theory, statistical decision theory, you have loss functions, you have number of data points, you have complexity of the space, you have all kinds of interesting constants that are related according to all kinds of equations. You never see the word runtime. So you'll have the number of data points, but that's not a surrogate for runtime. The whole field of computer science is to take the number, like n, and turn it into something like n log n or n squared or something like that. So that's missing in computer science. Similarly, in statistics. In computer science, similarly, complexity theory of all of its variations, you won't find the word risk. All right? You will find other objective functions like worst case geometric error and so on, and a number of clauses that were not solved and so on. But you won't find statistical risk. So, and it's hard to put the two together. In particular, the lower bounds in these two fields don't talk to each other. Sometimes the algorithms talk to each other, but the fundamental things you need to understand the problem in a deep way just don't go together easily. So we still have a lot of challenges here. All right, so in my group, the last 10, 15 years, we've been working on these kind of things. And I'm going to give you some little, really, vignettes. I'm not trying to sell anything. There's not going to be some procedure I want you to use for certain problems, but I want you to sort of show you how you might think about these problems. And in some ways, these are thought experiments. What if I try to put these two things together? How do I think that through so that I could deliver an answer? And then maybe we could argue about how to make it better and so on. So I picked privacy just because the story is nice to tell, and you actually get out a little engineering rule of thumb of how to do private data analysis that has theoretical justification. I'll say something similar about kind of Shannon theory, where sort of Shannon theory doesn't give us all that we want, but by adding something to it, we can get what we want. And then I'm going to talk a little bit about let's call it the variational perspective, and you'll see what I mean when I get there. Okay, so this is joint work with John Ducci and Martin Wainwright at Berkeley. John's moved on to Stanford. And I don't think I have to say much about the setup here. I think you all know about this. People are gathering data about us all the time, and we might have privacy concerns about the data. And when you get the lawyers involved, they'll sort of say, well, you either just can't use that data at all, or it's open public data, so if you're fine to use it as much as you want. And that's not where we want to be as a society. We want to be able to have sort of knobs that we say, well, I'll reveal a little bit of my data depending on the problem you're trying to solve and maybe other incentives. So if you want my genome, for example, I might say, well, what inferential problem are you working on? Is it to solve a disease that runs in my family? Then have my genome. Right? If it's to set insurance rates, well, maybe no, or maybe a little bit. I think it is good to set insurance rates, so I want to have my data a little bit. Or if it's to sell me something, advertisement, then maybe no. But I want a knob to set, and it depends on the inferential problem being solved. And all of us want that knob. And so as a data analyst, I've got to collect data from you, taking into account that each of you have set a knob at a certain way. We have a contract that I agree to protect your privacy at a certain level. I'll take your data, and I'll do the best inference I can do with that. And I want to quantify how good my inference will be given the knobs that you've set. Right? That's the kind of challenge we have to face, to be real about this problem. Okay, so let me make a couple of diagrams which will help to bring this home and also hopefully make this computational inferential thinking distinction clear. So let's be database people for a minute. Classical database has been collected. It has maybe bank accounts in it. I've got people. I've got their, their age, where they live, and I've got how much money they have in the bank and so on. I have a good old-fashioned database. So I can put in a query to it, like, for example, what's the maximum account size or the median or something like that, and I can get out an answer, which I'm going to call theta twiddle for reasons that will become clear here in a minute. So some answer comes out to my query. Now, there's a beautiful computational theory, kind of probabilistic computational theory that's been developed. Several of them have been developed, but differential privacy is what I'm going to focus on, where I can make guarantees that there are procedures, let's call them channels, that will take in a database and smudge it up in some way, obfuscate it, add noise to it, such that I get a privatized database, and I can make guarantees that I can't assert that someone was in the database if I've just looked at the privatized database, for example. Okay? And I can do this over all queries in some family of queries, and I can get out an answer, let's call it now theta hat, and I can guarantee that theta hat is close to theta twiddle under all queries and under all databases, okay, in some family. So this is a nice theory. It's been developed. I'll say a few more words about it in a minute. All right, now, so I would call this computational thinking. You figured out what the computation you need to do is, and you solve the problem at some level. The inferential story is different. So now let's think about the inferential problem. Shift it over a little bit. Query comes into a database, out comes an answer. The inferential person is always trying to think about where did the data come from? All right, and what am I trying to say something about the data in the database, or am I trying to say something about where did the data come from? So let's take a different example. Let's suppose this is now medical data. All right, and so it's people and their age and height and weight and maybe their blood pressure, and then I gave them a treatment or not, and how long did they live? Kind of a typical medical database. All right, now do I want to protect the privacy of the people who gave me that data? Probably yes. I probably want to make some guarantees to them. I'll protect them. Right? But am I interested just in the specific people in my database? Like I was in the banking example. I'm interested in how much money each person has in my bank. I don't care about other people who aren't in my bank, maybe. Here, probably not at all. In fact, imagine these people are dead and gone. All right? But that data is still really useful because I'm going to use it to predict for some brand new person who comes into my doctor's office how long they're going to live if I give them the treatment. That's what you collect medical data for. You don't collect it for the specific people in the database. All right? So I would call that an inferential problem. Now, what you're worried about is a population behind the data. There was a sampling pattern that gave rise to the database, and you've got to worry about that sampling pattern. And you can put a query into the population, meaning you ask the same question of somebody new who wasn't in your database but could have been. All right, and you get an answer, theta. And now the statistical theory, 300 years of statistical theory, will be able to tell you that theta will be close to theta twiddle with high probability over all populations P, over all sampling patterns in some family, and over all queries in some family. That's the kind of theory you get there. All right, so I hope you can see where I'm going. Now, the real goal is to glue the two together. Okay, so I want to now collect data, yes, and privatize the data, so I make guarantees to the specific people who gave me their data. But I don't care about those people. I care about the people like them in some underlying population. And I want theta to be close to theta hat. I don't care about theta twiddle at all. I want theta to be close to theta hat, again, with high probability over all Q, over all P, over all S, and over all queries. Okay, so that's the kind of problem that you don't see people addressing because they're kind of in the computational pipeline or they're in the statistics pipeline. And this is kind of, to me, the real problem. Okay, so with John and Martin, we've worked on this problem. I just want to give you our kind of attempt to make this some mathematics out of this and to actually give rules of thumb that you could use in a real private inference setting. Okay, so let me say, I have to say what I mean by inference as a theoretician. So this is just good old-fashioned decision theory. Wald, econometrician, statisticians, started this. There's a family of distribution script P that can be some arbitrarily big family, and there's some descriptor of a particular P, theta of P. See if I can get a little thing to show you that a little better. Here we go. So let's call it a parameter. All it means is some functional of the probability distribution. So P is the truth that generates the data, and this is just maybe it's a tail probability or a quantile or some other descriptor of the distribution. I want to estimate that theta with a theta hat, and I'm going to now define a loss function which measures how unhappy I'll be if the truth were theta and I were to output theta hat. Okay, so from Wald's point of view, this theta is random because it was based on the data, and the data is random. So I can take an expectation over the data where P is the true generator of the data. So this is the same P in here and here. Okay? All right? So compared to, say, computational theory, where you typically would do worst case sort of things, critically here there's an expectation. And sometimes in computer science you worry about, well, what average case? With respect to what distribution? Well, here it's with respect to the same p that you're trying to infer things about. Okay? So you take this expectation, and this object now is called the risk. And the risk is a function. It's the risk function. It's a function of p. So if we had a one-dimensional space of distributions, then this would be just a curve of some kind. Okay? And it's also a function of the specific procedure you're using. I might have my preferred procedure. Fayshaw has one. And so we're going to compare risk functions. He'll have a risk function. I'll have one. If mine is always lower than his for any value of p, then I just sort of win. My procedure is the best thing to do. But often they will cross. And so Wald was aware of this, and he said, okay, what we're going to do is study, we're going to define now the minimax principle, going back all those years ago, and still very useful to this day. Now we're going to get kind of worst case. We're going to take a supremum now of an expectation. So there's your still pretty statistical framework, but now we've taken a supremum. So kind of robustness, if you think of this as robust Bayes, if you will, kind of with the worst prior, an adversarial setting. But anyway, that object now is called the maximum risk, okay? And now the p is gone because we've took a supremum over it. This is now just a number for any given procedure. All right, now it's a number that's a function of all the other statistical constants of the problem, like the number of data points and the dimension of the problem, d, n, and so on. And for particular problems, people have worked this out over all the decades. So this number typically goes as 1 over square root of n, or 1 over n, or 1 over n to the 1/3. And d appears as either log d or d, and so for various problems, this is now all worked out. So the mathematics is, typically a few pages of operating on this little optimization problem here, and getting upper bounds and lower bounds and trying to get them to agree, and so on and so forth. Okay, so let's just assume that all that theory has been done, and now try to think about the privacy setting, where we now have private data, x1 through xn. That's each one of us in this room. We have our own private data. We're going to put it through a channel, q, and the smudged up output of the channel, z, is going to be sent to the central statistician at Google to do the data analysis, and we're going to be all happy with that. All right? So the estimator is based on z, and the private data actually came from, is the x's that came from p that we're trying to do inference about behind the scenes. Okay, so what is this differential privacy idea? It's kind of a likelihood ratio idea. It's really kind of has a lot of statistical content to it. It's just a fact about the channel. There's no p here. There's no data. This is just about the channel. All right? And so what we're going to do is look at the output of the channel and ask, is that output in some set that some adversary picks, any possible event that an adversary could pick, under x being the database or x prime being the database. So x could be the database with me in it, x prime is the database with me not in it, and this might be a database of criminals. So I'm very interested that you don't know that I'm in that database or not. Okay, so after all events you could test as an adversary at the output of the channel, this ratio is very, very small. So there's kind of a band around that likelihood ratio. If that's really, really small, then you have no statistical power for detecting I was in the database or not. You can't assert in court, oh, I know he's in the database because it was very low this probability is very different between x and x prime. Okay, so it's just a likelihood ratio criterion, kind of a uniform sense. All right. Now we get a knob to turn here. If I set alpha equal to 0, then I'm insisting on very strong privacy. Alpha 0, I get a 1 here. That means the likelihood ratio is the same whether I'm in the database or not. So you really can't distinguish at all. But if I turn alpha up to like a half or 1 or bigger, then I'm allowing a little more kind of wiggle room where there'll be some small differences between the output with me in it or not, but maybe not enough for you to really detect reliably that I'm in the database. So that's differential privacy. So now let's put that into contact with statistics. Okay, let's do statistics with privacy guarantees. Okay, so all this changed here, the same setup, but now we have this new family of private channels that guarantee privacy at level alpha. So all we're going to do is here this big colored long equation here, but none of it's new to you guys because we talked about the risk, that was the expectation, over the estimator and the truth. The estimator is based on z, and the truth is based on p. But anyway, it's an expectation over those things. It's the worst case, like Wald told us to do, so there's the maximum. And then it's minimax. I took the minimum, the best procedure under the worst case risk. So everything from the blue on is very classical. All we've done is turn this into a new constraint optimization problem by adding in it further, find the best channel among the set of channels that guarantee privacy at level alpha. So very natural setup, right? And call that the private minimax risk. Now the whole question is, can you do the mathematics that gives you rates? How does this go as a function of n? How does this go as a function of alpha? That's be the critical. And can we get alpha and n appearing together in the same equation? Now we're getting an inferential quantity and a computational quantity together as a design tool. Okay, so let's take a particular example to make this more concrete. Let's suppose people are coming into hospitals and they abuse various substances. So here's somebody who abuses alcohol and cocaine and none of these other things. And let's suppose that in the underlying population in all of Los Angeles, here's the actual rates. There's 45% of people abuse alcohol and 32% cocaine and so on. This seems realistic to me. Now, if I'm a public policy person, I want to know these numbers because these are really meaningful numbers. This will tell me how many hospitals to build and how many doctors put in each hospital and those kind of things. So it's really important to get these things right. All right? If I'm a classical statistician, I just gather data like this, and I take sample proportions, and those are uniformly good estimators. They're maximum likelihood estimators of these things. All right? All right? But no one wants to give me that kind of data because of privacy concerns. All right? So what am I going to do? All right, well, first of all, I'm going to do the mathematics to find out the best I could do, the lower bound. All right, so this talk is a lot of this is about lower bounds. So let's get lower bounds in a realistic situation. We're trying to estimate this set of proportions. It's just the mean of the distribution. We're going to work with this L infinity norm. If you don't know what that means, it just means the worst. I want to make sure everybody is handled correctly, not some 95%. So it's a stringent norm. And let's be non-parametric. Let's take all distributions supported on some compact set, not some special class of distributions. In that setting, this is a classical result. If in a first semester graduate level statistics class, you learn this, that it goes as 1 over square root of the number of data points. And dimensionality of that vector appears in the numerator in that way. All right, so now that was gotten by taking that infimum of the supremum and actually doing some mathematics with that, calculating covering numbers and using Fano's inequality. All right, so what happens if we now add that extra infimum with alpha? So do we get alpha in the equation? And the answer is yes, we do in a beautiful little place. It occurs right here. It sits next to the n, okay? And so what is alpha? So suppose that I set my person, you ask me, I tell you, what's your inferential problem? I'm studying some disease. I say, okay, for that one, I'll set alpha to be equal to half. Okay, I want some protection, but not too much. And you say, okay, that's fine. I multiply half, I square it, I get a fourth, and that multiplies the number of data points. So the effective amount of data now is n times a fourth. So all I got to do is collect 4 times as much data, and I achieve exactly the same risk as I had before in the non-private setting. And I would know that a priori. I'd tell you, here's my problem. Okay, you can give me your data. Yeah, with alpha set to that. So I just say, okay, I'll go collect 4 times as much data. I'll just spend more money. I get more data. So this is the kind of rule of thumb that I want for real-life people building real-life systems. They would be able to make guarantees for people about their privacy, but also make a guarantee that I can get the risk down to some tolerable level. All right, it's a design principle. Before you saw any data, you knew how to do it. You have to go hope and cross-validate and try things out. All right, now this result, it turns out that n goes to n alpha squared and then d appears up in there, actually occurs generically for a wide range of problems we've analyzed, not just this problem. So we actually propose this as a law of private data analysis. Okay? It's not completely universal, but it's a law that you can use in many, many problems. And it kind of comes out from a kind of a Taylor expansion of a certain covering number. It's for generic reasons. It's not all that surprising that it comes out when you start to do that mathematics. All right, so now that's a lower bounds. This is the best you can possibly do. Is there some procedure that achieves that lower bound, or is this just kind of meaningless mathematics? That's always the next step. So let's try to actually work out a mechanism. So here's back to my private data. Maybe someone abuses alcohol. I guess that was heroin. And so I want to privatize this data. So what you usually do in this literature is you add Laplace noise to the data. You add independent Laplace noise. Laplace noise is heavy-tailed noise. If you add Gaussian noise to data, you can provably show that you're not protecting privacy. It's not heavy-tailed enough. Okay? If you want to protect privacy, you can add Laplace noise, and you can provably show you will protect privacy. Okay? So it's widely used in the database community. All right, now, but we're trying to do something more. We're trying to do this inferential problem. If you add Laplace noise, how much do you damage the inference? A little bit, a lot? Do you reach the lower bound? And the answer is you damage it a lot, way too much. And so you're not even close to the lower bound. Okay? So this mechanism, while it looks good kind of from a differential privacy point of view, is actually damaging if you're trying to use this for statistical inference. So is there some other mechanism that's better or actually reaches the lower bound? And the answer is yes, there is. So here it is. So here's the private data again. And so what we're going to do is it's going to seem kind of ad hoc, but it's optimal. So what we're going to do is we're going to toss a coin. We're going to define a random bit vector. So maybe it came up to be 0, 1, 1, 0, 0. Well, then we'll take 1 minus that. All right? And now I'm going to transmit to you, the central statistician, the closer of v and 1 minus v to the actual data with probability that depends on alpha. So alpha comes into play right there. So if alpha is equal to 0, so I'm not protecting privacy, I'm very stringent, this is 1 over 1 plus 1, it's a half. So I transmit random. I transmit v or 1 minus v equally probable. I'm not giving you any information. So good, I am protecting privacy there. But if alpha is bigger than 0, then I'm leaking some information to you. I'm giving you something that's just closer on average to the truth than the other vector. All right? So this, you may sort of say, well, yeah, you're transmitting information, but this is pretty weak. You're not giving the statistician much information here. But that intuition is actually wrong. You're actually giving them optimally transmitting information in this problem. So this is with real data from the drug abuse warning network in L infinity error. As the sample size is getting up to about 60,000, this is the ad-Laplace mechanism. So your error is high, and this is that optimal mechanism, and this is on a log scale, so this is extremely significant differences. Okay? So this is what you really would want to do for this problem as a way to privatize and transmit information to the central statistician. Okay, so that's all I wanted to say about that. It's a little vignette. Again, it's kind of a thought experiment. Can I do mathematics that brings privacy together with inference? And answer is yeah, you can. And moreover, you get out answers that in a wide range of problems. So I talked about multinomial estimation, but in a whole bunch of other problems, it turns out this is a sort of generic result that brings together the constants from statistics, n and d, with the constant from differential privacy, the alpha. All right, let me briefly turn to a second example just to give you the flavor that you can do this sort of thing in other areas. So again, this is with John and Martin, but also with Yuqing Zhang, talking about compression being brought together with statistics. Okay, so that was privacy. Let's think about now another externality, compression. All right, so didn't Shannon kind of tell us how to do compression? Is there anything left to do? And well, no, in the following sense, that Shannon told us how to compress to keep the average number of bits small. But if I want to compress and then do data analysis, Shannon didn't address that problem. So let's try to address that problem. All right, so the picture is going to look very similar to before. We're going to have data now it's going to be on multiple machines. There's going to be M machines. All right, and there's so much data, or maybe there's administrative barriers, so that I can't transmit all that data to a central site. All right, so instead I'm going to have to compress the data through a channel, X to Z, and I do so because there's a bit rate constraint from Z down to the central statistician. So I'm going to make guarantees that I can respect the bit rate, but still ask to do good inference. So how can we do that? All right, so here's the picture. I'm going to have a compression protocol that's going to be guaranteeing that I'm transmitting no more than B bits along that path, and doing so under a particular loss function and a particular set of parameters distributions. Okay, so here's our new problem we're going to solve. So we're using the L2 norm here. It's just more common in compression instead of the L infinity. So that's our loss function. We take the expectation, we get a risk. We take the maximum, we get the maximum risk, and we take the infimum, we get the minimax risk. So that's that blue on, it's just the minimax risk. And now we do the same thing as before. We take a further infimum now, not over private channels, but over channels that guarantee a bit rate below B. Okay? And now if we can do the mathematics on this object here and reveal equations that relate N and D and B and everything, so we have some design principles. Okay, so let's again take an example. Let's just suppose we're just trying to estimate the mean of a very big Gaussian where we have data distributed over M machines, and I and J are run over the huge data set that has components M and N. Okay, so the classical minimax risk in this problem, because it's the L2 norm, goes as 1 over the total amount of data. If there are M machines and there's N data points on each machine, NM is the total amount of data. So this is the fast parametric rate you get in this kind of problem. So this is, again, an easy exercise in a first semester statistics class to find that out. Now, what happens when we add the bit rate constraint? Can you do the math? And the answer is yes, you can. And out comes an answer like this. The minimax rate now is upper bounded by the same answers before, right there, 1 over NM. And now all these other constants come into the problem this way. You get logarithm of the number of machines. That's pretty good. That means you can have lots of machines and you don't pay too much cost in terms of risk. Right? And then B and D do occur together in this very nice way. So that's the minimum of B and D. All right? So D is the statistical dimension of the problem. It's the number of the components of the vector you're trying to estimate. And B is the bit rate. So why are those two so close together? Well, that's a discovery, really. We didn't know that. It's not obvious that that should have happened. Right? And so what it means is that if you've decided already you're going to estimate D components, that's given to you by the problem statement, and you could pay more money to make B as larger and larger and larger, get more bandwidth, then what do you want to do? Well, you might want to set B equal to D, all right? And then the minimum B and D just becomes D, and they cancel above and below. And so now you get a result which is independent of dimensionality. I can get the risk to be independent of dimensionality by just paying enough money to have my bit rate high enough. Okay? That doesn't mean my risk is independent of n. It goes down as 1 over n. But it makes it independent of dimensionality, which is pretty interesting. So this is not something that comes out of Shannon theory. Shannon theory does not address this. It's a new discovery that comes when you put statistics together with compression. Okay, so I could go on about that. There's a few other problems we've looked at with this kind of constrained optimization and statistical problem with another externality coming from other fields. And I encourage those of you who are interested to try to play this game. It really, it's been very productive. All right. So, all right, but in the last part of my talk, I'm going to turn to the mother of all problems, really, is try to put statistics in contact with computation. We did it for communication and privacy. What about computation, more broadly speaking? All right, so now this is going to be hard. I'm not going to be able to tell you how to do this. So first of all, what do we mean by computation? Well, in some sense, Turing gave us an answer for that, a very useful answer, very broad answer, but maybe too useful, too broad. It's hard to, so Turing, for example, had a theory in which 2 tape machines and 1 tape machines were the same, all right, because there's a polynomial transformation between the two, right? But if you start to use that theory in the context of statistics, it'll turn out all those n's and d's will differ between the 2 tape and the 1 tape machine, all right? So you don't get out, that it's not the right formalism for thinking about lower bounds in statistical inference problems. All right, so you have to kind of think of maybe a more restricted definition of computation, and I think we don't have one. So in some sense, we're waiting for another Turing or Kolmogorov or someone to come along, maybe one of you, to help us with kind of the right notion of computation for the purposes of inference. Now, that doesn't mean people haven't been trying, and so there's a whole bunch of ways to think about this. So one of them is to use geometry, and my first piece of work on this whole topic was with Venkat Chandrasekaran, who's just down the road at Caltech, trying to relate, so you can relate runtime to convex geometry. That's kind of known as relaxations, and taking like a semi-definite program and reducing it to a linear program and so on. There's known effect on the runtimes. And if you can relate geometry to risk, then you can relate runtime to risk with this intermediate of geometry. And so we had a paper doing that. We developed a little bit of a statistical theory on relating geometry to risk, and we're to bring, but that's for a very restricted class of problems. You can also pull out of the database world all the beautiful ideas on concurrency control and try to make parallelism your computational knob to turn, and use concurrency control to control risk. So there's a whole bunch of work at Berkeley on doing that in various settings, and the work is ongoing. Then probably the most productive of all, I think that many of us who work on this kind of theoretical side of machine learning have been exploiting, is the notion of optimization as computation. So just for a typical example of that is that if my computational problem is just to minimize functions. I'm not trying to do everything, but I'm going to minimize functions. All right, so I'm going to let you see the gradient of a function k times. You can choose anywhere you want. You can choose any arbitrary k gradients of a function. Having done that, what's the best you can do in terms of getting close to the minimum of the function? Right? And is there an optimal rate that you can do that, and are there procedures that achieve that rate? All right? So that style of thinking has been extremely productive, probably the most productive area. And then there's all kinds of other approaches that I could talk about. My favorite one probably is subsampling, where ideas that include that Amit and others were involved, Bag of Little Bootstraps, and some others that we've been working on lately, involving kind of the obvious idea where you take a big data set, you break it into small pieces, and worry about still the inferential consequences of doing that, not just run them separately, glue them together, and it runs faster, or I'm done. You got to worry about, did I get as good of a risk? All right, but what I've decided to do is that we had some brand new work that just got published like the last couple of weeks that I'm real interested in about optimization oracles and lower bounds. All right, and I think that this topic is broad enough interest that I'm going to talk about it instead. So I don't even have PowerPoint slides. I'm going to go to another set of slides, if I can find them, that are there. I love when that happens. Isn't that fun? So I did this talk once before at Princeton, and so you guys are the second ones to hear it last week at Princeton. There it is. And so these are in PDF slides, and I'll just have to eventually get them into one talk. Yeah. Okay. So first of all, this is joint work with Andrew Wibisono and Aisha Wilson, who are grad students at Berkeley. Real experts on optimization. So, worry about my time a little bit? I'm fine. All right. So let me just sort of make a broad philosophical statement. This word variational is really, really important to me. So When you learn physics, the first way you learn it is you learn about Newton's equations, F equals ma, right? And so you learn about differential equations. That's a differential equation. And now what's the computation you do on differential equations? You integrate them. So you learn about numerical integration eventually if you study enough physics. Okay? So integration is the computational tool. And integration came over in statistical inference. It's the computational tool of choice by many people. It leads to Markov chain Monte Carlo, and so on. So it's definitely, been very, very prominent. Lagrange, about 100 years later, a famous Italian, and despite the name, he's Italian, came along and said, well, Newton's equations, which involve integration, you can actually get exactly the same physics by turning the physics problem into an optimization problem, not an integration problem. He wrote down a functional called the Lagrangian, and said if you and integrated that, right? And said if you optimize that, you get out some curves. And those curves are the same ones that you get out by integrating differential equations and doing them locally along the paths. Exact same physics come out. And probably the Lagrangian perspective ended up winning out because it led to quantum mechanics and so on. All right, and now another variational problem is eigenvectors, right? So what's an eigenvector? Well, ax equals lambda x. That's an algebraic definition, okay? So it just says here's a system of equations and here's the answer is there. All right, so there's another perspective, which is that you write this as a solution to an optimization problem. You write down x transpose ax divided by x transpose x. And you find the best x that does that. All right, now by turning to an optimization problem, there's now an optimization curve that you're trying to minimize. And if you can't solve that problem, you can solve an easier problem by changing the optimization curve, and maybe the solution only moves a little bit. So that perspective is the perspective of variational thinking in general. Okay, so whenever I see kind of people writing down solutions to problems, I say, wasn't there a principle behind that, like variational principle? Isn't there an optimization problem that was maybe perturbed in some way that led to that? It's not, especially if you start getting differential equations. All right, so now why do I bring this up? All right, well, there's been this beautiful line of work going back to the Russians starting in about 1983. So we're going to be talking about convex optimization. This also applies to non-convex, but I want to just kind of keep this clean for this talk. So we're doing minimization over a convex function f, all right? Now, I hope you all know about classical gradient descent. It just says you go downhill, you pick the steepest descent direction, and let's assume an oracle was able to tell you the best amount to step along that direction, and you just move along. Right now, it's not that hard to analyze this under this convex setting and find that you get a rate. This goes down as 1 over k, okay? So is that fast? Is that best? Is that optimal? Well, no one really knew. In 1983, Nesterov came up with a new algorithm, all right, that has two pieces to it. It has a y and an x, all right, and the y part looks like it's doing gradient descent. It is kind of doing gradient descent, and then the x part kind of looks like it's kind of taking a little bit of the past and putting it together with the future. So it's kind of a momentum kind of interpretation. These pair equations amazingly achieve a faster convergence rate than gradient descent. So that seems kind of surprising. This is the optimal direction. It's the optimal step size. Right? But there's a better algorithm that's also kind of local. It goes much faster. So this is called acceleration, and not enough people know about this. This is really one of the big discoveries in applied math, in the last 30 years. Now, many people have stared at these equations and tried to understand them. All right? And I'm not going to try to explain them because there's some intuitions, but none of them are the right intuition. They don't lead to the full explanation of this phenomenon. And I'll try to make that more clear in a couple of slides. All right? But anyway, the point of this part of the talk is going to be that that's not the right set of equations to look at. All right? There's some underlying principle. There's the right place to be looking for this. All right, to summarize, though, what happened after Nesterov is all kinds of other gradient methods were developed that were accelerated. So Nesterov started with gradient descent, but then you could do this to mirror descent, another kind of descent methodology. You could do it to Newton's method, and there's a whole bunch of others. So it's been very important for theory. You get optimal notions of optimality, and then there's many beautiful extensions that have been very practical in recent years. These methods are not descent methods. They actually go downhill and they go back up, and they go downhill and they go back up, sort of interestingly. They're faster than gradient, and they're still mysterious. So there have been a whole bunch of papers, and I love a lot of these papers, but I should say you should read all of them, trying to interpret this. They're kind of like momentum methods. They kind of have a heavy ball interpretation. There's a beautiful paper by Moritz Hart interpreting them as Chebyshev polynomials for the case of quadratic functions, but not for general convex functions. I like this geometric shrinking idea of Sebastian Bubeck. And anyway, these are all recent papers, so people are still trying to understand this mystery of what is acceleration. Okay? So these are nice, but they're only applicable to first-order methods or strongly convex functions. They're not the general story. All right. So what is the underlying mechanism that generates this? What is this phenomenon? All right. So it turns out you need to go to continuous time, first of all. So you do not understand this phenomenon by working in discrete time. Okay. So if you're a computer scientist used to discrete your whole career, there are moments in life where you have to go to continuous to get a deeper understanding. Calculus is going to be needed. All right, so here's your first, if you haven't seen a differential equation before, here's a differential equation. It's called gradient flow. It doesn't have a beta there. The beautiful thing about continuous time, you don't have to have a step size. Okay, so it just take the gradient at a point, take the negative of that, and that's your derivative, and you integrate along the differential equation. Okay, and if you discretize that, you get out gradient descent. All right, so there was a very nice paper, Sue, Boyd, and Candice from Stanford wrote this paper where they took Nesterov's equations, that pair of equations, and they took a limit where the time step went to 0, and out pops a second-order differential equation. Okay, so here it is. This is a very now kind of famous equation. So it's non-homogeneous, and it's second order. Okay? Right? And they studied this equation, and they were able to kind of solve it in certain situations, understand some of the oscillations, and get some insights. Right. Now, whenever you see a differential equation, you should think, is there some underlying object which is generating a differential equation, just like Lagrange did for physics? All right. So that's what we're going to do. We're going to show that there's an underlying deeper mechanism. We're going to develop a general variational approach that will understand essentially all existing variational algorithms, or acceleration algorithms. All right. And the key to this is actually there's a discretization methodology needed to get the fast rates. The differential equation has the rate, but if you discretize in the wrong way, you lose the rate. And so what Nesterov's insight seems to be, from this interpretation, is actually how to discretize a certain system of differential equations. So that's pretty interesting. Okay, so here it is. I'm just going to write it down. Here's the underlying principle. So, so there's a whole bunch of pieces. Let me start to break up the pieces. So it's an object that's a function of curves, so of a position, a velocity, and time. All right, there's kind of a constant out front. These are just kind of like rate functions. Let's not worry about them for now. This is an object that's real important. It's called the Bregman divergence. It's a Bregman divergence between x and x kind of perturbed by a little bit of a time derivative. Okay? Bregman divergences are generalized notions of distance, where the distance between x and y is gotten by taking a generating function h, all right, dropping a tangent to h, and taking the difference between where the tangent predicts you are and where the h function predicts you are. That amount there is the Bregman divergence. If this is a quadratic function, this just gives you Euclidean distance. So it's a generalization of the Euclidean distance. Okay, so we're putting the Bregman divergence here, and we're subtracting off the function we're trying to optimize here. So it's got these two pieces, a little bit like a classical Lagrangian in physics. All right, and in fact, if you're in the Euclidean setting, the h function becomes the quadratic, and you get literally a kinetic energy. So this looks like kinetic minus potential energy. All right, now we have these little rate functions here. So it turns out we've been able to define these things we're calling ideal scaling conditions, that if you set alpha to t in a certain way, which I'll tell you about on the next slide, then beta t and gamma t are determined by certain conditions. These conditions are those required to get acceleration. If you don't impose these, you get curves, but they're not the fast curves. All right, so what is calculus of variations? It's I don't know, 300-year-old discipline. It came as soon after calculus. So here's this function. It's a functional at an instantaneous time t. You put that in an integral, integrate over t, you get a number, and you optimize that over curves, x. So here's a certain curve. This might be the optimal one. Here's another one that's not optimal. Okay? And in calculus, you set all the partial derivatives equal to 0. The continuous time version of that is called the Euler-Lagrange equation. This is the same as set all the partial derivatives equal to 0, just in continuous time. This object here, again, some apologies for the math here, but I really think the young people in the room should be aware that this kind of math is part of your future too. Some of you took computer science to avoid differential equations, but they will be part of your future. This is a differential equation. It's a derivative of this object. Various derivatives are taken, but at the end of the day, it's just time changes. So it's a differential equation. And in fact, if we plug in our Bregman thingy up here, our Bregman Lagrangian, then we take this, do this here, we get this equation. Here's our master equation. It's a second order equation. It's non-homogeneous. It's got the x dot here, and then it's got some stuff that involves the gradient. So it kind of looks like an object that might have something to do with going downhill of f in kind of an oscillatory way. All right? Okay, so I'm going to try to close up here. I don't really want to run too long. I want to tell you but I got maybe 3 more minutes, and I'll be closing up. So, all right. So I'm going to there's a paper on this in the archive. I'm just not going to get into all the mathematics. I'm going to go over some mathematics somewhat quickly. So anyway, can you prove things about this? Well, one of the beautiful facts about being in continuous time is that it's easy to get rates. In discrete time, you got to do kind of pages of calculations, and it's hard to get rates. Here, here's the rate proof. 2 lines. You write down a Lyapunov function, you take its first derivative, and for that to be negative, you have to have a certain condition, which is exactly that right there. Okay, so I'm not getting into details here, but if you're ever trying to analyze rates of algorithms, you know that can often be a challenge. When you're in continuous time, sometimes it can be trivial, and it's trivial in this case. So we get this rate, which is it's exponential rate, but in this beta function. Right? So can we realize that? Can we go exponentially fast? Right? That doesn't seem very plausible. Turns out in some cases you can. Right? All right, but we're not probably expecting that. So our first little example is here, we're going to not expect that. We're going to try to go at logarithm of t, and then we take the exponential, we get polynomial rate. Because we're kind of expecting it goes like 1 over k or 1 over k squared, not e to the minus k. All right, so let's just set beta to that. And then alpha and gamma were determined like I told you. And now you get out this differential equation, and this starts to look very similar to the Su, Boyd, and Candice equation. Right? And in fact, they got 3 over t. If p is equal to 2, we get 3 over t here. And in fact, if p is equal to 2, this whole thing simplifies, and it is the Su, Boyd, and Candice equation. Okay? So in the general case where we have a general h, it's this other paper. And in the Su, Boyd, and Candice case, when this h is Euclidean, we get their equation. So this generates their equation. So we got acceleration. And in fact, we got acceleration in this case. That's for p equals to 2. Okay? All right? Now, it turns out that we can also set p equal to any integer. And we will get out algorithms that actually go at rate 1 over k squared, k to the third, k to the fourth. We can actually go as fast as we want. And that's a new discovery. All right, so the last 1 minute is we now have this general master differential equation. All right? That's in continuous time. To put this on the computer, you have to discretize. How do you discretize? So if you ever really studied physics seriously, you learned about Hamilton's equations and like the stellar mechanics. How do you actually build physical simulations? Right? And that's a whole field of its own. There's tons of textbooks on everything. And naive approaches generally don't work. And so it turns out here also the naive approaches don't work. So if you try to take this equation and apply what's called Euler discretization here, it actually gives you unstable equations, not just bad ones. And they lose the fast rate. All right? So I'm just going to, this slide says that if you discretize, it turns out you get these equations. I'm not getting into details. Here's a pair of equations you get. And when you run them, they can start to converge and they shoot off to infinity. They start to converge and they shoot off to infinity. So they're unstable. You would never use these. Is there a way to discretize these things that is stable and still keeps the accelerated rate that we got in continuous time? And there is, and it involves adding an extra sequence here. And what we're doing in doing this setup here, again, the math is flying by, I don't expect you to understand it, is we're mimicking what Nesterov did in his little setup. We took the inspiration from his style and we put it in this framework. All right? And then it gives you provably the fast rates, and they're stable. So there may be other ways to discretize, but this turned out to be one that gives you everything. So I'm going to finish up here. There was other things I kind of could say if I wanted to cram stuff in. I'm not going to do that. To get higher order, all these high order rates here that goes as k to the p power, you can get them by this equation. This is a master equation for getting arbitrary fast rates. And I want to skip over that. But you get rates of k to the p out of this framework at this point. Okay, so I'm going to skip and go to the end. So here's a summary slide, which is gradient flow can actually also turn out to be sped up. You get these slow rates, t to the p minus 1 instead of the p. And if you discretize them, you get k to the p minus 1. So this is kind of known that if you can go to higher order gradient methods, you get this. And what's new in this paper is we're able to get this fast rate t to the p, not t to the p minus 1. And when we discretize in this particular way, we get k to the p and not k to the p minus 1. Okay, so I'm going to skip over this part and just finish up here. So the summary of this little part, again, that was fast, but I'm excited by this. I think there's lots to do with it. I wanted to show people, is that there's this object we're calling a Bregman-Lagrangian now, which is worthy of study of its own. Where does this object come from? You know, does it have gauge invariance? Does it have other nice physics-y kind of properties? It turns out you can get exponential rates, actually. If you have uniform convexity, you can actually prove this rate. You can study other properties of this object, and you can also define, if you're a physicist, you'll know that for every Lagrangian, there's always a Hamiltonian, and this thing has some other nice properties to be studied. Okay, so part of the reason I went through this is that so I become more of a theoretician over time. I was really an applied person trying to make machine learning things do cool things. That is kind of what is happening these days. There's a lot of companies based on making machine learning do cool things. And I think that's great. I think that should go on. But I think as we start to do that, we also have a responsibility to be engineers and make guarantees and say theoretical statements about things, especially as things get distributed and asynchronous and complicated. We got to start to develop a civil engineering of data. And so to me, it means being a theoretician. And so I become more of that over time. So if you were thinking about being a theoretician, you think all the theory is done and dead. That's not true. Not true. So both the systems and the AI and the theory are very alive these days. And it's the interactions of them. So if you're a computer scientist, go learn some statistics. If you're a statistician, learn some computer science and learn how to make them come into interface with each other. And of course, with all the applications in mind. So thanks for the attention. That's all I wanted to say. The what?
In the first half of the talk, you care about how close theta hash is to theta.
Yeah.
And here in the second part of the talk, you care about the function values. So can you apply the second part to your theta rather than the function values?
Well, this is an optimization story here, and there's a lot of work that other people have really done about when you get close to an optimal solution to an optimization problem, what implications does that have for statistics? Okay, so that's not, in fact, my work, that's others. But if you were to try to tell the story you're trying to tell, that's what you would do. You'd say, I can now get to the bottom of a hill at a certain rate in a certain way, and that tells me something about risk, and so we can start to stitch this story together.
Will accelerate function value increase.
Yeah.
Will that accelerate the closing to the...
Yeah, that is a fantastic question, and I could sort of say it's been answered, but in a long line of work by lots of people and lots of papers. And there's not just kind of one way to answer it. If you put Lipschitz condition, you can make certain kind of guarantees and other conditions as well. So it's a whole interesting area of its own. Function values versus argmins.
Any other questions?
Yeah.
I cannot see for the life of me how you have a gradient, and then without assuming anything about the family functions for which you want to do the optimization,
Yeah.
just by doing some hocus pocus, you get accelerated and all this, you must put some,
Yeah.
you don't get something from nothing.
Yeah. So when I went on sabbatical in Paris about 4 years ago, I hadn't learned about Nesterov's work. And one of the things I wanted to do while I was sitting there in cafes in Paris was to understand it. And so he has a nice little thin book that I read about 5 times sitting there, and I got it. And I encourage you to do it. It's something really very deep about that. Yeah. It does. There's a theorem that proves it. No. I said nothing empirical today. Everything I said here is rigorous and it's got theory behind it, not just mine, but others. And Nesterov is beautiful theory. And if you haven't seen it yet, it's really worth the time because it's a new idea. It's not just a consequence of some tweak of somebody else's theory. There's a avowedly new idea. I should say the complexity theory analysis, the oracle theory behind this is not just Nesterov. Nemirovsky is another important name in this. Yudin and Nemirovsky have a beautiful book on the oracle complexity of optimization and achieving lower, defining what you mean by lower bounds, and then the achievability has been many, many people. Yeah, first order, that's right, for first order. But yeah, it's an evolving, beautiful discipline, and no, you're not getting something for nothing, but there's mathematical structure there that people didn't understand before. Yes?
So, I'm not really an expert on this, but it seems to me that if you take an inherent disabling method, like gradient descent, and you turn it unstable,
Yeah.
but then put an active controller on top of it, which monitors instability and kind of brings it back into the stable regime, then you could do better in terms of achieving the minimum faster. Is that the basic idea?
No. I mean, that's a beautiful way to think, and in fact, one way you can think about all these things is you can take the underlying Hamiltonian or Lagrangian, discretize that. Don't go to differential equations at all. Discretize that. You get what are called Hamilton-Jacobi-Bellman equations, and those lead to dynamic programs. All right, and those can preserve properties. For example, if I want to integrate a physical system and do it numerically, but conserve energy, that along the discrete path, I conserve energy, which you want to do for real physical systems, right? You do what are called symplectic discretizations. They work directly on the underlying Hamiltonian. Predictor corrector methods have the flavor of control loop around these things, and all of this has to do with optimal control. Hamilton-Jacobi-Bellman comes up in optimal control. So there are lots of connections here, but I would not do what you suggested as I don't think that's the interpretation. I think these are actually kind of symplectic. I think Nesterov's approach was actually symplectic. There's a geometrical explanation for that, which I don't think I could really explain. I don't know it. I don't believe it's clear right now, but I think that's what it is.
Any other questions? Okay.
So assume I'm the pool.
I can't see you because there's a huge light right behind your head. You look like the savior.
The pool engineer at the beginning
Yeah,
of the slide.
yeah.
How should I actually tell them all the things to my boss, or maybe educate my boss that okay, I'm doing it right?
Yeah, that's a great question. So I just think, so other fields have done this. The people who built airplanes that fly through the air, I can guarantee their bosses don't understand all the, how lift works. And how, you can guarantee that the plane is actually stable and all that. But somehow that field emerged kind of, a dialogue, a way to explain ideas and give guarantees. And I mean, there's a lot of math. I didn't show you that much math today, but under the hood here, there was a lot of math that you would never show your boss. But I would show them something like d divided by square root of n and try to convince them that, and alpha, and convince them they can understand that. And I'd also like to even convince providers of data, you and me, that we can understand alpha. We can intuit what that means. And so there's little parts of we have to ask everybody to get more quantitative, right, without taking calculus classes. You have to learn a little probability, a little bit about, just like we learned how to do a little bit of basic economics. All of us have learned a little bit of, right? So we need to do that. But yeah, there's when I'm arguing, especially for a young audience, I think it's really important that all this AI and data science and all this is not like over or done and now is the gold rush era. This is like decades to work on to make this real. And indeed, that includes being able to talk to CEOs and talk to presidents who are even dumber than CEOs.
So if I may.
Yes.
So I actually have a simple answer to that question. Just encourage your boss to go to YouTube or video lectures, look at watch Michael's lectures. So I think we have time for one last question over there.
Yes.
Do you have a high school student who's going to choose between the major in mathematics, statistics, physics, computer science? What would you say to choose first? What to study first?
Yeah. Now, that's a wonderful question. At Berkeley, I've been involved in the design of a brand new course for freshmen. If you go to databears.berkeley.edu, it's our attempt to teach a class on what we call data science for freshmen, assuming no calculus and no probability and no computing. All right? And about halfway through the class, they learn how to do permutation tests on non-parametric hypotheses. They learn how to do regression, put error bars on predictions. They learn how to do data visualization. They learn how to do classification. And they do this all in Python. And they do it with real data. All right? And they love it. We had 500 students taking it, and they were raving, ratings through the roof. So I actually think that you can get some of the kind of principles here, the ones I alluded to, permutations, non-parametrics, bootstrap, blah, blah, regression. Usually that's taught at the end of grad school, if at all. All right? That's ridiculous. You can understand that at the freshman level, even without any mathematical preparation. And once you understand those principles, you can turn them around and say, well, what mathematics do I need to understand those? Instead of just let's learn on years of calculus and eventually be able to do it. All right, so I don't think it's easy to give the answer to your question, which is what does a random individual do? But our system has got to reshape itself to put statistics first, calculus later, is one thing that would definitely help. And no more statistics that's just t-tests and formulas that are based on asymptotics that aren't real and no one understands. And, but permutation tests, bootstraps, things like that, that bring computing together with statistics. That's the way to go. Thanks.
All right. Thank you.